Hey everybody, welcome to our third video lecture. Our topic for today is spherical coordinates. With spherical coordinates, we describe yet another way to represent the position of points in three-dimensional space. Of course, we already know two other ways to represent points in three-dimensional space. The first of which is Cartesian coordinates. Here, the position of a point is described by a triple of values x, y, z. And this is probably the coordinate system that we're most familiar with. Last time, we introduced a second coordinate system called the cylindrical coordinate system. Here, instead of a triple xyz, we're representing a point by a triple r theta z. Spherical coordinates are even cooler. Here we represent a point by a triple rho, theta, and phi, where phi, like theta, is another angle. The descriptions of a point in either Cartesian or cylindrical coordinates are some things that are already very familiar to it. In particular, the point xyz is described by going over x on the x-axis, going over y on the y-axis, and looking at where the corresponding point crosses, then going up from there a value z, and then I get to the point xyz. The point r theta z in cylindrical coordinates is obtained by going over theta in the angle and going over from the origin by r, and then going up from there by a value z, and we get to the point r theta z. For spherical coordinates, theta will play the same role as before, but rho and phi are going to do some slightly different things. In particular, if I'm in three-dimensional space and these are my x, y, and z axes, then the point given by the spherical coordinates rho, theta, phi is the tip of the vector which makes an angle phi coming down from the z-axis, this angle phi here, and which has a length of rho. So the length of this vector is rho, and whose projection in the xy plane has an angle with the x-axis, which is given by theta. So to summarize, rho here represents the distance of the point from the origin. Theta represents the distance, or the angle of the projection of the vector into the xy plane from the x-axis, and phi represents the angle of the vector from the z-axis. Algebraically, I can see that the z value of this point is given by the right triangle that I can form. So this is the corresponding z value. And if I think a little bit about my trigonometry, this means that z is given by rho times cosine of the angle. The projection into the xy plane is a vector in the xy plane whose length here is given by the other side of that triangle. So we know that that's going to be rho times sine of phi. So that's the hypotenuse of the corresponding right triangle in the xy plane. The x value is given by this side of that triangle. And if we do a little bit of trigonometry again, we get that x is given by rho times sine of phi times cosine of theta. And similarly, y is given by this side of the right triangle in the xy plane, which is going to be the hypotenuse times sine of theta. So y will be given rho times sine of phi times sine of theta. And this set of three equations tells us how to convert from a point in spherical coordinates to a point in Cartesian coordinate. So let's try to do an example. Let's try to convert the point 3 pi over 3 pi over 6 from spherical coordinates into Cartesian coordinates. Here remember that the first entry is rho, the second entry is theta, and the third entry is phi. Our x value is then given by rho sine of phi cosine of theta, which is 3 over 4. Y is given by rho times sine of phi times sine of theta, which is going to be 3 times sine of pi over 6 times sine of pi over 3, which is 3 root 3 over 4. Finally, z is given by rho times cosine of phi, which is just going to be 3 times cosine of pi over 6, which is 3 root 3 over 2. So that does it. That's the corresponding point in Cartesian coordinates is x equals 3/4, y equals 3 root 3 over 4, and z equals 3 root 3 over 2. Now just like with cylindrical coordinates, certain shapes are much easier to express in terms of spherical coordinates. For example, let's figure out the shape described by rho equals 4. In particular, this will be some sort of surface in three-dimensional space, and our question here is, what surface is this? Now we know how to recognize surfaces in Cartesian coordinates, so it makes a lot of sense here to try to convert everything back into Cartesian coordinates. Now let's think a little bit about how to do that. If we think for a minute back to our picture of spherical coordinates, rho here was the distance of a particular point from the origin. So I know how to convert from a point x, y, z in Cartesian coordinates over to a point in spherical coordinates, at least as far as rho goes. Specifically, rho is going to be the distance of the point x, y, z from the origin, so rho is going to have to be equal to square root of x squared plus y squared plus z squared. Theta is playing the same role that it did before for cylindrical coordinates, so our equation for theta will work the same as before. Specifically, theta is going to be inverse tangent of y over x. Finally, to get what phi is, I can remember that z is this side of this right triangle. So I know that rho times cosine of phi will have to be z. And that allows me to write phi down as inverse cosine of z over rho. Since we already have an expression for rho, that just tells us that phi is equal to inverse cosine of z divided by the square root of x squared plus y squared plus z squared. So this allows us to convert an equation that's in terms of spherical coordinates into an equation which is in terms of Cartesian coordinates. Specifically, our equation rho equals 4 is now going to become the square root of x squared plus y squared plus z squared equals 4. And if I square both sides here, this is given by x squared plus y squared plus z squared equals 16. And we should definitely recognize the kind of equation that this is. This is a sphere of radius 4 centered at the origin. This is really nice because it's sort of analogous to the result that we found for cylindrical coordinates. In cylindrical coordinates, when I set r equals to a constant, I got a cylinder. In spherical coordinates, when I set rho equal to a constant, I get a sphere. Let's think about another example. Here I've got the equation rho squared equals 9 over the quantity sine squared phi minus cosine squared phi. And I'd like to figure out what surface this describes in Cartesian coordinates. To start out, let me go ahead and clear the denominator and rewrite the expression as rho squared times sine squared minus rho squared times cosine squared equals 9. Now if I remember my picture again for spherical coordinate, I can see right away that z is going to be given by rho times the cosine of phi. That means that this term over here, given by rho squared cosine squared, is going to be the same thing as z squared. The second term, or the second part of that triangle, shows me that this expression r here, which is the corresponding radius in the xy plane, in other words, the typical point in cylindrical coordinates, not spherical coordinates, is going to be given by rho sine phi. So I should be able to express rho squared sine squared as r squared. So my equation converts to r squared minus z squared. And if I remember that r squared is x squared plus y squared, the expression that I'm getting is x squared plus y squared minus z squared equals 9. I'm not sure I like how well that green shows up, so let me rewrite that expression in a different color. But we all know what that looks like. That's a one-sheeted hyperboloid centered on the z-axis. One of the most important applications of spherical coordinates is it allows us to integrate certain expressions that would otherwise be very difficult or impossible. To integrate in spherical coordinates, though, we need to figure out an expression for a typical volume element. In other words, we need to figure out what an appropriate expression for the Jacobian is, just like when we're doing an integration in terms of polar coordinates or cylindrical coordinates. A typical volume element looks like a Cartesian product of the sets, or rather the intervals, going from rho to rho plus d rho, theta to theta plus d theta, and phi to phi plus d phi. This generates a volume which is almost cubical, but has a little bit round edges, given by this blue colored region here. If I look at the way that its shadow the shape that the shadow makes in the xy plane, I can see that the side length here on this rightmost side is going to be rho sine theta times d theta. This is because the same thing is happening to the shadow. The side of the shadow here will be rho sine theta d theta because the length from the origin is rho sine theta and the angle that we're changing is d theta. So that's just the length of that arc. The length of this side is simply d rho because I'm moving from distance rho to rho plus d rho. And finally, using the fact that this is an arc length as well, given by changing the angle from theta to theta plus d theta, the length of this side is going to be rho d theta. So the total volume element is given by dv equals rho squared sine of phi times d rho d theta d phi. And this actually tells us how to integrate. Specifically, if we consider a solid region E consisting of all triples in spherical coordinates rho, theta, phi, such that phi ranges between alpha and beta, theta ranges between g1 of phi and g2 of phi for some functions g1 and g2, and rho ranges between h1 of theta phi and h2 of theta phi for some functions h1 and h2, then we can re-express the triple integral over the region E of some function f of xyz as an iterated integral with everything in terms of spherical coordinates. Specifically, the triple integral over E of f of xyz dv is the iterated integral, first from alpha to beta, then from g1 to g2, then from h1 to h2, of f, but with x, y, and z all switched to spherical coordinates, so x becomes rho sine phi cosine theta, y becomes rho sine phi sine theta, z becomes rho cosine phi, multiplied by rho squared sine phi d rho d theta d phi. And this component right here is something that we've seen both in terms of converting integrals to polar coordinates and also converting integrals to cylindrical coordinates, and here we're seeing again, and this is called the Jacobian of the transformation from Cartesian coordinates into spherical coordinates. And depending on the on the transformation, we'll have a different Jacobian each time. So for cylindrical coordinates, our Jacobian was just r. For spherical coordinates here, we see the Jacobian is much more complicated. And we'll talk about Jacobians a lot more later on when we think about more arbitrary transformations. But we can remember this as just being the Jacobians for spherical coordinates. And what it came out from was our analysis of that typical volume element in spherical coordinates. So now let's consider an example. In this example, what I want to do is find the volume of the solid region within the sphere x squared plus y squared plus z squared equals 4, above the xy plane, and below the cone, z equals the square root of x squared plus y squared. To start out this problem, I want to draw a picture. To start out, let me draw that equation, x squared plus y squared plus z squared equals 4, which is a sphere of radius 2 centered at the origin. The next thing I want to do is I want to draw that cone, z equals the square root of x squared plus y squared. This is going to be a cone which is centered around the z-axis and growing larger as z gets larger and larger. So it looks something like this, and it intersects with the sphere at some particular value of z. To figure out what that value of z is, I know that on the cone, z squared is equal to x squared plus y squared. And also on the sphere, x squared plus y squared plus z squared equals 4. So if I put that all together, I see 4 is going to be equal to 2 copies of z squared. So that'll say that z squared is equal to 2. So on that intersection, z is going to be equal to plus or minus the square root of 2. And it's definitely going to have to be the plus 1 because we're up above here. So this intersection is happening at z equals the square root of 2. So I think a good next step would be to try to convert all of these different equations into corresponding equations in spherical coordinates. The sphere is particularly easy. I know that x squared plus y squared plus z squared is rho squared, so the equation of that sphere is that rho squared is equal to 4, or more simply, rho is equal to 2. The equation of the cone is also pretty simple. We can find it a couple different ways. One way is to simply say we're always at a particular fixed angle, phi, so this is going to be given by phi equals something. We can also get it just by substituting things in directly. So if I remember what z is in terms of spherical coordinates, z is given by rho times cosine of phi. X is given by rho times sine of phi times cosine of theta, and y is given by rho times sine of phi times sine of theta. So I end up with this expression. If I simplify this, I get rho times cosine of phi is equal to rho squared times sine squared of phi times the quantity cosine squared of theta plus sine squared of theta. And if I remember that sine squared plus cosine squared equals 1, this just gives me the equation rho times cosine of phi is equal to the square root of rho squared times sine squared, which of course is just rho times sine. So I end up with in the end that cosine of phi has to be sine of phi. This is exactly when tangent of phi is equal to 1, or when phi is equal to pi over 4. So my surfaces have exceedingly simple descriptions. And now I should remember also that my sphere intersects the xy plane in a nice circle of radius 2. So what I'm trying to do here is find the volume above that circle, that green circle there, and below that orange cone that I'm drawing in here. Now that green circle is part of the xy plane, which has the equation z equals 0. If I remember that z is equal to r times cosine of phi, this is saying, not r, but rho times cosine of phi. This is saying that rho times cosine of phi must be 0. This is going to give us that cosine phi itself should actually be 0. So this xy plane is described by the equation that phi is equal to pi over 2. That makes sense because that's thinking about all the points whose angle from the z-axis is exactly 90 degrees. And that's going to be the xy plane itself. So if I put all this together, I'm thinking about going from the angle phi equals pi over 4 to phi equals pi over 2. And I'm thinking about going from radii, rho equals 0, all the way out to rho equals 2. And in terms of theta, I'm going full circle this way. I'm allowed to go from theta equals 0 to theta equals 2 pi. So to describe the region that I'm interested in terms of a nice set, it's very easy. The set that I'm interested in is the set of values rho, theta, and phi, so that rho goes between 0 and 2, theta goes between 0 and 2 pi, and phi goes between pi over 4 and pi over 2. So I can re-express the integral that I want to do. And for this problem, I just wanted to figure out the volume. To figure out the volume, all I'm going to do is I'm going to integrate the function 1 over the domain of interest. When I integrate 1 over that domain, that just produces the volume of that domain. So by the theorem that we wrote above, this is going to be equal to a triple integral of 1 times rho squared sine of phi d rho d theta d phi. And my outermost bounds here are my bounds on phi, so those should go from pi over 4 to pi over 2. My middle bounds here are my bounds on theta, so those should go from 0 to 2 pi. And my innermost bounds are my bounds on rho, which are going from 0 to 2 in this instance. This is a really easy integral to do. The innermost part, I'm just integrating rho squared. So this is the integral from pi over 4 to pi over 2. Integral from 0 to 2 pi of 1/3 rho cubed times sine of phi, evaluated from 0 to... Oop, and I have a typo here. The innermost bounds were supposed to be from 0 to 2, and I wrote 0 to rho for some reason. 0 to 2. Evaluating that from 0 to 2, d theta, d phi. So when we evaluate this, we get 8/3 times the integral from pi over 4 to pi over 2, and the integral from 0 to 2 pi of sine of phi d theta d phi. This is just 16 pi over 3 times the integral from pi over 4 to pi over 2 of sine of phi d phi, which in turn is minus 16 pi over 3 times cosine of phi evaluated from pi over 4 to pi over 2. Of course, cosine of pi over 2 is 0, and the cosine of pi over 4 is the root 2 over 2, so this becomes 16 pi over 3 times the square root of 2 over 2. So that was a nice first example. As a second example, just getting the mechanics worked out, let's try to figure out the integral over e of x squared plus y squared dv, where here e is just the region in between the spheres x squared plus y squared plus z squared equals 4, and x squared plus y squared plus z squared equals 9. And just like all my problems, I want to start by drawing a picture. These are spheres of radius 2 and 3, respectively, that are both centered on the origin. So I'm looking at trying to describe the region that's between these two spheres. It's not limiting my angles at all, so my angle theta should be allowed to go full circle from 0 to 2 pi. The angle phi should be allowed to fill its full range as well, but phi never goes from 0 to 2 pi. We can access any particular coordinate in terms of spherical coordinates by just allowing phi to range from 0 all the way to pi. So my phi ranges go from here to here, because if I want to get another point on the back end, I can just rotate my other angle instead. So my phi ranges are always between 0 and pi or less. So I can express my set E here as the set of all rho, theta, and phi values, where phi is constrained to be between 0 and pi. Theta goes between 0 and 2 pi. And rho, well, let's think about that. Rho needs to be somewhere outside the sphere of radius 2 and somewhere inside the sphere of radius 3. So it needs to describe a point whose distance from the origin is between 2 and 3. So that means that rho is going to have to go itself between 2 and 3. That's perfect. I've got a description of the set E I'm trying to integrate over, and now I just need to set up the integral. So the integral that I want to do is just going to be an integral from 0 to pi, and from 0 to 2 pi, and from 2 to 3. And I'm going to integrate x squared plus y squared. But I need to convert x squared plus y squared into spherical coordinates, and whatever it becomes, I'm going to be multiplying that by rho squared sine of phi d rho d theta d phi. So let's think about it here for a second. X squared plus y squared, I can either substitute indirectly in my expressions for x and y in terms of rho and theta and phi, or I can use the fact that x squared plus y squared here is really that r squared value in cylindrical coordinates, which is a certain hypotenuse of a triangle in spherical coordinates. In particular, one of the equations that we've used several times already is that x squared plus y squared is going to be equal to rho squared times sine squared of phi. So I can replace x squared plus y squared with rho squared sine squared, and this is the integral that I'm trying to do. The innermost integral here is easy. Integral from 0 to pi, integral from 0 to 2 pi, and I'm integrating rho to the 4th, so it's going to be 1/5 rho to the 5th times sine cubed of phi. I'm evaluating that from 2 to 3. d theta d phi. Oh, and I have a bit of a typo here. It was 1/5 rho to the 5th. So this gives me 211 over 5 times the integral from 0 to pi and an integral from 0 to 2 pi of sine cubed phi d theta d phi. There's no dependence on theta here, so integrating from 0 to 2 pi just multiplies by 2 pi. So this gives my integral to be 422 pi over 5 times the integral from 0 to pi of sine cubed phi d phi. And maybe you're scratching your brain at this point trying to remember how to integrate sine cubed. And if you are, that's okay. But one of the nice things that we can do here for sine cubed is you can remember this trig identity that sine squared is equal to 1 minus cosine squared. So I can rewrite this integral as 422 over 5 times the integral from 0 to pi of 1 minus cosine squared of phi times sine of phi d phi. And I'm just remembering that 1 minus cosine squared is sine squared, so this is really sine cubed in here. And now I'm going to go ahead and do a u substitution. U equals sine of phi. In that case, du is equal to cosine of phi d phi. Oh, sorry, I've got this backwards, don't I? I want to instead do the u substitution. U equals cosine of phi. So that du is minus sine of phi d phi. Because I've got a nice sine of phi d phi term right here, so that's going to make everything turn out really well. So my integral then becomes the integral of 422 over 5. And I've got my integral, and this 1 minus cosine squared, well, u is cosine, so this is going to be 1 minus u squared. And sine of phi d phi is just minus du, so I've just got a negative 1 times a du term. And that's a nice easy integral to do. And my bounds of my integral I can get now from using the fact that, when phi is equal to 0, u is equal to cosine of 0, which is 1. And when phi is equal to pi, u is equal to cosine of pi, which is minus 1. So this is really the integral from 1 to minus 1. And if I take that negative sign into account as well, I can just write this as 422 over 5. Ugh. Integral from minus 1 to 1 of 1 minus u squared du, which is a nice easy integral to do. It's going to give us 422 over 5 times 4/3. Alright, let's go ahead and try out one more example. Here I want to evaluate the triple integral over e of x times e to the x squared plus y squared plus z squared dv, where here e is the portion of the ball x squared plus y squared plus z squared less than or equal to 1 inside the first octant. And this equation here makes a ball precisely because of the inequality. If this was an equality, we just get that sphere of radius 1. Because it's inequality, we're getting all the points whose distances from the origin are less than or equal to 1, so it's giving us that full ball there. So for us, what E is E is this quarter chunk of the top hemisphere of a ball of radius 1. So my angles theta are allowed to go from theta equals 0, which is just the x-axis, to theta equals pi over 2, which is 90 degrees from the x-axis, or the y-axis there. My phi terms are allowed to go from phi equals 0, which is the z-axis, all the way through phi equals pi over 2. And my z values are going from the origin, and they're allowed to go all the way out to that surface of the sphere. So my rho values are allowed to go between 0 and 1. So the expression of my set E as a set is it's the collection of all triples, rho, theta, and phi, so that so phi is going between 0 and pi over 2, theta is going between 0 and pi over 2, and rho is going between 0 and 1. That means we can write down the integral that we want to do as an integral from 0 to pi over 2, an integral from 0 to pi over 2, and an integral from 0 to 1 of our expression, whatever it happens to be, times rho squared sine of phi d rho d theta d phi. And to get our expression here, I need to convert x times e to the minus, or not minus, x e to the x squared plus y squared plus z squared into spherical. Now in spherical, I know that x squared plus y squared plus z squared is very easy. It's just rho squared. And x itself is going to be rho times cosine of, sine of phi times cosine of theta. So that's our expression for the x term. And the e to the x squared plus y squared plus z squared is just e to the rho squared. So this is a nice easy expression in there for that. So this is the integral that we're trying to do. And everything in this integral is a product, so I want to show you guys a nice neat trick here. One thing we can do is I can separate out, in terms of dependencies, all the integrands. So I can write this then as an integral from 0 to pi over 2, integral from 0 to pi over 2, integral from 0 to 1 of rho cubed e to the rho squared times sine squared of theta times cosine of phi d rho d theta d phi. And because these are products and none of the bounds on the integrals, all the bounds on the integrals are constants, this is actually equal to the product of these three separate integrals. Integral from 0 to pi over 2 of sine squared phi d phi, integral from 0 to pi over 2 of cosine of theta d theta, and the integral from 0 to 1 of rho cubed e to the rho squared d rho. Not that you have to do it that way. If you want to do it just as an iterated integral, business as usual, everything's going to work out just fine that way too. But I think this is a nice fun little trick to be able to pull off here. Now to make the first integral happen, I'm going to convert that sine squared into the integral from 0 to pi over 2 of 1/2 minus 1/2 cosine of 2 phi d phi. That second is very easy. It just becomes sine of theta evaluated from 0 to pi over 2. And then the last integral is a little bit tricky. To do that integral, we're going to want to do a u substitution. U equals e to the rho, or u equals rho squared. In that case, this integral is going to become the integral of u e to the u times 1/2 du. And we're still integrating from 0 to 1. To finish that integral off in the end, we're also going to have to do integration by parts. So that one is a bit of a journey. But this first integral is very nice. It's just giving us pi over 4. Is our final answer there? Our second integral is nice as well. It's just giving us 1. And our third integral now, after a little bit of integration by parts, is u e to the u minus e to the u evaluated from 0 to 1 times that 1/2 term. So when I evaluate everything all together, I'm just going to end up with pi over 8. So we've done quite a few examples of some integrals in spherical coordinates. We've shown that some integrals that if we started out here, for example this one, if I just tried to do this in Cartesian coordinates, I really might end up with quite a bit of headache. So spherical coordinates are a very useful tool. They're allowing us to do some calculations that we'd otherwise have quite a bit of a struggle with. And we've looked at some examples of that. We've looked at how spherical coordinates are defined, and we've looked at how spherical coordinates make the expressions of certain shapes, which would otherwise be very complicated, quite simple. For example, the equation of a sphere just becomes rho equals a constant. So that's a very nice thing. The equation of a cone also similarly becomes phi equals a constant. So that's a very nice equation too. But I think that's a pretty good stopping place for now. Next time we'll pick up by talking about change of variables, and we'll talk about a little bit more about that Jacobian construction that we were alluding to before, and kind of see how that works more generally. So I'll see you guys next time.